In the previous video, we were introduced to Newton's toolbox equations, a set of relationships between the fundamental kinematics quantities that apply when acceleration is constant. In this video, we will apply them as a demonstration of how to solve physics puzzles. This course is about more than physics. It's about developing a way of analyzing physics puzzles. In this class, every physics puzzle is solved in the same basic process. And that means this process will be one of the most important things you see in this series. Let's apply the process to this puzzle. A car is at rest on an open road. It accelerates at a constant rate of 3 meters per second squared until it reaches 39 meters per second. How long did the acceleration take? The first step in solving any physics puzzle is to draw a picture. This is needed for 3 reasons. First, it forces you to visualize the situation described in the puzzle. Physics puzzles are not math problems. They correspond to something that occurs in real life. The picture is proof that you understand what is taking place in the puzzle. Second, it is a psychological aid. If you are stuck on a puzzle, you can always revisit the picture to ground yourself. Third, I will take off points if there is no picture. Step 2 is to clearly show the endpoints of the motion. Remember how a few videos ago we examined the motion of an object by taking 2 photos of it at 2 different times? The endpoints clearly label on your picture where the object is when the first photo was taken and where it is when the second photo was taken. Here, we've superimposed the 2 photos so there's less to draw. Step 3 is to clearly set the origin and axes for the situation. This establishes where we are starting all the measurements from and which direction is positive. Now, the motion of the car doesn't depend on how you set your axes, so you could set your axes whichever way you want as long as you stay consistent. The right way to set the axes is whichever way makes the problem easiest to solve. Often, that means placing the origin at one of the endpoints and pointing the positive axis in the direction of motion, but there are exceptions. Here, I've placed the origin at the back bumper of the car when the car was in its initial position, and I've set rightwards as the positive direction. Step 4 is to list the unknowns. Remember, there are 5 kinematics variables. We have to return to the question and see what was being asked to identify which of these is the unknown. How long did the acceleration take? That's asking for a time. So time is the unknown here. Step 5 is to list the known quantities. Remember, each kinematics equation contains 4 of the kinematics variables, so you will need to be given the values of 3 of the kinematics variables in the question. It accelerates at a constant rate of 3 meters per second squared. That's an acceleration. Until it reaches 39 meters per second. That's how fast it's traveling when the second photo was taken. That is its final velocity. We need a third known value. Look at the first sentence. A car is at rest. That is another way of saying the initial velocity is 0. So now we have 3 knowns. Step 6. Find the equation that relates the knowns to the unknown. The unknown is time, while the knowns are acceleration, initial velocity, and final velocity. Out of the toolbox equations, there's only one that uses these 4 specific variables. That's equation 1. So that's the one we have to use. Step 7, the last step. Substitute the knowns and solve for the unknowns. The acceleration is 3 meters per second squared, initial velocity is 0, and final velocity is 39. Simplify and isolate time. We get time equals 13 seconds. So that's the solution. It takes 13 seconds for the car to increase speed from 0 to 39 meters per second if the acceleration is 3 meters per second squared. Equivalently, you could say that 13 seconds elapsed between when the first and the second photos were taken. Now, suppose I provide the same situation, but I ask a slightly different puzzle. Instead of asking how long the acceleration took, I ask how far did the car travel until it reached its top speed, starting from rest. For this new puzzle, the drawing, endpoints, and axes are the same as before, but in step 4, where we ask what the unknown is, that's where things change. How far did the car travel? That's asking for a displacement, not a time like what we did earlier. In step 5, the knowns are the same as before. But in step 6, things once again change, because we need a different equation, one that weaves together displacement, initial velocity, final velocity, and acceleration. Equation 4 is the only one that will do that. Step 7. Substitute for the knowns and solve for the unknowns. The acceleration is still 3 meters per second squared, initial velocity is still 0, and final velocity is still 39 meters per second. 39 squared is 1,521. 0 squared is, of course, 0. And all that equals 2 times 3 times displacement. Simplifying and dividing both sides by 6, we get a displacement of 253.5 I hat meters. That's the displacement that the car experienced between the two photos. We have now solved 2 kinematics puzzles. I should perhaps point out that 39 meters per second is 88 miles an hour, and the car we've been following is indeed a DeLorean. Consider this situation. A child is in a sled. Initially, the child is moving at 2 meters per second, but the acceleration of the sled is negative 0.25 meters per second squared. How long does it take for the child to travel 6 meters? We begin this puzzle by drawing a picture, the same way we begin any other puzzle. Here's the ground. Here's the sled. And here's the child. Now, in this situation, we take a photo at the child's initial position, and we can take a photo at the child's final position. Now, let us see what we know in this situation. Because the child is traveling from left to right, we can set our origin at the front edge of the sled like this, and we can set rightwards as being the positive direction. We were asked for how long it would take for the child to travel a distance of 6 meters. So the thing we're being asked for, the unknown in this circumstance, is the time. But the displacement that occurs between the two photographs is 6 I hat meters. The initial velocity of the child is 2 meters per second, again in I hat, and the acceleration is negative 0.25 I hat meters per second squared. So using this information, displacement, velocity, acceleration, we need to find the time. Let's go ahead and do this. The only equation that weaves together all 4 of these quantities is toolbox equation number 2, which reads like this.
delta x is equal to v initial times t plus 1/2 acceleration times time squared. So let's plug in what we know. The displacement is 6 meters. The initial velocity is 2, time is unknown, plus 1/2 times an acceleration of 0.25 meters per second squared times t squared. Let us simplify this somewhat. Half times negative 0.25 will give us negative 0.125, and this whole equation can be rewritten like this. Negative 0.125 t squared plus 2t minus 6 is all equal to 0. This is a quadratic equation, which means we can solve it using the quadratic formula. The quadratic formula says negative b, or the time to be more specific, will be equal to negative b plus or minus square root of b squared minus 4ac, all over 2a. Notice that when I write a over here to reference the coefficient of the t squared term, I'm writing it without a vector symbol, so we don't get it confused with a meaning acceleration. Now let's plug in what we know. Negative b plus or minus square root of b squared minus 4a c, all divided by 2a. Now, this mess that we have over here has to be calculated, and a calculator might come in handy. So, the square root of 2 squared minus 4 negative 0.125 times negative 6 gives us 1. So we now have negative 2 plus or minus 1 divided by 2 multiplied by negative 0.125, which is negative 0.25. So the possible solutions to this would be negative 2 plus 1 divided by negative 0.125, seconds, or negative 2 minus 1 over negative 0.125, which would be 12 seconds. In this case, the 4 seconds is correct. The 12 seconds would only apply if the child had eventually kept moving after photo 2 was taken, eventually come to a stop, and then started moving backwards. So t equals 12 seconds is a solution that makes mathematical sense, but it's not one that makes physical sense.
The toolbox equations are very well suited for freefall, objects falling under gravity with zero or negligible air resistance. Near the surface of a planet, acceleration due to gravity is very close to constant and always points towards the center of the planet. On Earth, acceleration due to gravity has a value of 9.81 meters per second squared for any object towards the center of the planet. Of course, the value is different on other celestial bodies. Here is a coconut tree. A coconut, initially at rest, falls from the tree. It takes 3 seconds to hit the ground. How tall is the tree? We can solve this using our process. Step 1. Draw a picture. Here's a coconut tree. Step 2. Set the endpoints. The puzzle starts the instant the coconut starts falling from the tree. The puzzle ends just before the coconut hits the ground, maybe a nanosecond before. These are the points where we are taking our two photos. Step 3. Set origin and axes. For a bit of diversity, I will set the origin at the second photo near the ground, and I will set positive to point upwards. I know this isn't the easiest way to set the axes. I'm just using this approach to show that you would get the correct answer either way. Step 4. List the unknowns. The question asked, how tall is the tree? That's talking about displacement. Step 5. List the knowns. The coconut is initially at rest. That means V initial equals 0. It takes 3 seconds to fall. Finally, it's in free fall near the surface of the Earth. That means its acceleration is 9.81 meters per second squared towards the center of the Earth. Again, that's the negative direction, the way we've set our axes. So the acceleration is negative. Step 6. Which equation weaves together the unknown delta x with time, acceleration, and initial velocity? Equation 2. That's what we must use. Step 7. We now plug in all the information we have and solve. V initial equals 0, acceleration equals negative 9.81, and time equals 3. 0 times 3 is 0, so that term cancels. Half of negative 9.81 is negative 4.905, multiplied by 3 squared. Solving, we get negative 44.145 meters. In other words, the coconut tree must therefore be 44.145 meters tall. If I could offer a word of advice, if you ever decide to visit my native country of India, don't walk directly under any coconut trees.
In freefall questions, an object is pulled towards the center of the Earth, and there's nothing else acting on it. But the object can be thrown initially. Consider this variant on the previous question. A monkey is sitting in a 25-meter tall coconut tree. It then throws a coconut downwards at 7 meters per second. What is the velocity of the coconut just as it hits the ground? We approach this question in exactly the same way as before. We start by drawing a picture. In this picture, the monkey throws the coconut downwards. So initially, we look at the coconut just as it escapes the monkey's grip, and later on we look at the coconut a nanosecond before it hits the ground. So we could say that photo 1 is just when the monkey loses contact with it, and photo 2 is just before it hits the ground. Now we have set our photos, our endpoints. Let's figure out the origin and axes. To keep things simple, I will have the origin as being the bottom side of the coconut, and I will set downwards as being positive. This is in contrast to the last question, and this is the easier way to do it because this way the axis lines up with the direction of motion. Now, the unknown. We were looking for the velocity just as the coconut is about to hit the ground, the velocity as we take photo 2. That is the final velocity. But we do know that the coconut tree is 25 meters tall, so the displacement of the coconut was also 25 meters. And to be more specific about it, 25 j hat meters, since the object is moving in the positive y direction. The initial velocity of the coconut is equal to 7 j hat meters per second. And the acceleration of the coconut is 9.81 j hat meters per second squared. This is, of course, the standard acceleration for anything which is falling near the surface of the Earth. Now, we have a displacement, an initial velocity, and an acceleration, and we're looking for a final velocity. There's only one equation that weaves together those four quantities, and that is equation 4. Now, let's plug in all the information that we know. V final is unknown, but V initial was 7 is equal to 2 times the acceleration times delta x. So simplifying, V final squared minus 7 squared is 49 is equal to 2 times 9.81 times 25. That's going to work out to 490.5. Let's continue. Let's isolate V final. V final is equal to isolate it, we can add the 49 to both sides. And that is going to give us 539.5. So that's V final squared. So the last step is to take the square root of both sides. That'll give us V final is equal to, I can't take the square root of 539.5 in my head, so 23.23. So this is the final velocity of the coconut, or just before it hits the ground.
How about this one? You throw a rock upwards off a 25-meter cliff. It lands 3 seconds later with a speed of 23 meters per second. What was the velocity with which you threw it? Step 1. Draw a picture. Remember, you threw the rock upward, so it reached its peak and then descended until it landed. Step 2. Set the endpoints. We'll take the first photo a nanosecond after the rock leaves your hand, and the second photo a nanosecond before it hits the ground. Step 3. Origin and axes. To keep things simple, I will set the original height of the rock, just as you threw it, as the origin. We will set downwards as positive. Step 4. List the unknowns. What was the velocity with which you threw it? That means the velocity in photo 1, the initial velocity. Step 5. List the knowns. The displacement is 25 meters, positive since we set downwards as positive. The final velocity is 23 meters per second, again positive. The time is 3 seconds. Step 6. Find an equation that weaves the unknown initial velocity to the known displacement, final velocity, and time. That's toolbox equation 3. Step 7. Solve. Substitute the known information. We get 25 over 3 equals Vi plus 23 all over 2. 25 divided by 3 is 8.33. Multiplying both sides by 2, we get 16.67 equals Vi plus 23. Finally, subtract 23 from both sides. The initial velocity is negative 6.33 meters per second. negative because we said upwards is negative. In other words, you threw the rock with a velocity of negative 6.33 meters per second.
Here is a subtle variant on the last question. A rock is thrown upwards at 10 meters per second. How long does it take to reach its peak? We start in the usual way by drawing a picture. Here is a character, and here is a rock that he is throwing. And we follow this rock as it travels upwards to its peak. So photo 1 for this rock would be at the instant it gets thrown, and photo 2 is when it reaches its peak. The subtle difference between this question and the last one is that photo 1 and photo 2 are now at two different places. More specifically, photo 2 is now at the peak, whereas previously photo 2 had been at the landing spot. And that's because we're looking at a different kind of motion. We're no longer interested in how the rock lands. We're interested in the rock as it reaches its peak. Let us say that upwards is the positive y direction, and the origin is the height of the rock as in photo 1. The unknown in this situation was how long it takes for the rock to reach photo 2. However, we do know that it was initially launched at 10 meters per second upwards, and this would be in the j direction because it's along the y-axis. The acceleration, even if you're throwing it upwards, is still towards the center of the Earth, but towards the center of the Earth is downwards. Since we set our axes as upwards, positive y is upwards, that means the acceleration is negative 9.81 j hat meters per second squared. We just need one last piece of information. When the rock reaches its peak, it's no longer moving. That means that at photo 2, its velocity is 0. So, we now have three pieces of information: initial velocity, acceleration, and final velocity, and we're looking for the time. There's only one toolbox equation that weaves together these four quantities, and that's toolbox equation 1. So, let's plug in what we know. Acceleration, negative 9.81, multiplied by time is equal to v final minus v initial. So, negative 9.81 times time is equal to negative 10. So time is equal to negative 10 divided by negative 9.81. 10 divided by 9.81, since the negative signs will cancel each other, you don't have to put them into your calculator, gives us 1.02 seconds. So this is the time required for the rock to reach its peak. Sometimes you will have questions where they ask for an object reaching its peak followed by an object doing a landing. In those cases, you have to set a photo 1 and photo 2 separately for the peak and then separately for the landing.
This video showed the standard procedure for solving all physics problems. In the next video, we will see more challenging applications of the kinematics equations.